How's everybody doing? All enjoyed the first morning session, the keynote? Everybody's all woken up-ish? All right. So my name's Nick Jackson. I work as a developer advocate for a company called HashiCorp. And what I'm going to talk about today is the kind of the history behind software development. So where we've come from. All the way back from 1970, back in the real dark days, up to the present time, and then we'll take a little trip into the future with flying toasters and internet-connected absolutely everything. And we'll kind of look at a few of the sort of the common things that moved us through those decades, how we tested software, the languages we used, the processes and deployment, and hopefully that will give us an appreciation of where we are today and where we will be tomorrow. So first stop, 1970. So 1970 certainly wasn't the foundation of computing, but it's where I want to begin. Because I think it was 1970s that really set the scene for modern computing with the advent of the personal computer. It was kind of a decade of accessibility. So the mainframes that IBM had been pushing out in the 1960s had kind of started to slowly fade away. We started to see a rise of a lot of smaller companies in the industry. We started to see, like we do today, a lot of venture capitalists who are putting money into the industry. We were seeing businesses succeed, but we were also seeing businesses fail. And in 1971, we saw the foundation of the NASDAQ, which was a stock exchange designed purely for the trading of stocks around technology and communications. It was also the first stock exchange which was going to be fully computerized. Now, at the time IBM was still kind of cornering the market, they were providing software and hardware. They were trying to kind of keep these third parties out by locking down their systems. But in 1975 in Albuquerque in New Mexico, a little company called Microsoft was born. And Microsoft, their first product was BASIC, which was written by Bill Gates. And it was designed for the Altair computer system. But also, Oracle was born. And Oracle at the time, again, 1977, wasn't called Oracle, but it was designed to set up to kind of compete with IBM. So the IBM databases, Oracle thought, we can get in on this market. We can produce a product which is better. They also started building out ERP systems, so resource planning software, and the combination of this database and the resource planning software turned it into the absolute beast it is today. And of course, Apple. We can't talk about the 1970s unless we talk about Apple. And 1976 was when Apple, Steve Jobs and Woz, founded that company in the back of his parents' garage. So one of the fundamental things about the 1970s is that software starts to become more complicated. Because it starts to become more complicated, people start to look at it from a more academic perspective. So you get the release of the book Brooks's Mythical Man Month. If anybody's short of a Christmas list present for their boss, right? And I think the important thing, though, about this book is that it deals with an issue. And it deals with an issue that's still important today, and that is that as the size of the software grows, the number of bugs and defects don't grow at the size of the number of lines of code. They actually exceed it. And this is really interesting, I found as well, that I didn't even consider this until I started writing this talk, but open source was founded in 1970. In some way, I mean, Richard Stallman was actually starting to share the programs he was writing at MIT with the other university. But it was these personal computers. It was the personal computers produced by Apple, by IBM, that really started to shape the decade. So we started to look at the languages that are used, and we've got things like C and Smalltalk, Pascal, Fortran. a few of them are still familiar. I mean, C is still predominantly used. If you look at some of the statistics, it's still one of the most popular languages, certainly around embedded computing. And they started to have this explosion in languages. So Capers-Jones, in his book, his Technical and Social History of Social Engineering, he wrote that the explosion of programming languages seems to be more of a sociological phenomenon than for true technical need. The existence of so many programming languages makes the maintenance of legacy applications complex and difficult. Indeed, the life expectancy of a large application is sometimes longer than the life of the language used to create it. There's something in that. I mean, I could make a cheap joke about JavaScript. But this is the truth, right? There's probably been 10 frameworks created since I started this talk. I think we need to start to think about this. The industry doesn't ever seem to settle into a state of equilibrium. And then there's testing. So in the 1970s, it was predicted that roughly 50% of the effort and 50% of the total cost that went into producing a piece of software was in the QA cycle. It was about quality and testing. And because of this, it was identified as a real problem. So there was a book released, a book which is actually still in print today, The Art of Software Testing by Corey Sander, Myers, and Badgett. And they proposed these 10 points. So things like, do not plan testing effort under the tactic assumption that no errors will be found. I don't know about you, my software doesn't contain errors. And the probability of the existence of errors increases when errors are found. Now, the interesting thing about these 10 points is that I took these from the 3rd edition of the book, which was published a couple of years back. I had to poke around to see if I could find some of the earlier books. I found a 2nd edition, which was published in 2004. Exactly the same table. Now, while the execution of our software has changed, it seems that the problems haven't. And we get on to deploying software. So how would you deploy software in the 1970s? I mean, you had networks of sorts. Both TCP and FTP were invented as standards in the 1970s, but predominantly the method of deployment was that a compiled application would be copied onto a magnetic medium, floppy disk if you were lucky, potentially magnetic tape, and you'd have to physically take it to the machine for distribution. Can you imagine trying to do that with a 20,000 node cloud? So in the 1970s, it was all about setting the scene. It was about modern computing. But the 1980s for me was quite special. It was the decade that I learned to program. It was the decade where I received my first computer. But importantly for the industry, this rise in personal computing spawned a whole new era of businesses. It was the decade of outsourcing. So in 1980, the IBM PC was released. Microsoft released MS-DOS. Now, interestingly, IBM contracted Microsoft to write MS-DOS for the IBM PC. They didn't follow the principles and practices of previous decades where they were trying to lock things down. I think in terms of the evolution of where we are today, one of the most fundamentally important factors is that TCP/IP, the standard that was set in the previous decade, was adopted by ARPANET, the precursor to the internet, as the standard method for communication between machines. Now that's given us the wide gamut of possibilities that we have. We've got the ability that machines can communicate across this standard. And AOL was founded. They had the internet in 1983. I mean, in the 80s, my knowledge of the internet was from Hollywood classics like War Games. I mean, like, I couldn't even imagine the possibility of being able to connect my computer to the internet. But AOL was there, and they were providing a modem solution for the Atari 2600. But we had the complexity problem. It's back. So the million lines of code which defined an application in the 1970s is now 10 million lines of code. And this started to prove a problem in terms of quality. So what Humphreys produced, a model to try and analyze the suitability of outsourcing partners for the United States Defense Department. And he wrote his capability maturity model, which sometimes is actually still used today. So what he tried to do was define this criteria within which he could assess a business. So he had this structure of maturity levels, process areas and goals, common features and key practices. If we look at some of the things in like the common features, you've got things like commitment to perform, ability to perform, measurement and analysis, verifying implementation. And when you look at the levels that he was ranking these on, again, it's this 5-point scale. So you have from initial, the lowest level, and that's a definition of a process which may be ad hoc, it's chaotic, you've got individual heroics. So team effort was recognized again back then. But the results are the most staggering. 10% of all organizations that were surveyed during this study only managed to achieve average and above. Now that's quite staggering when you think about it. But if you take it into retrospect, as an industry, it was quite new. So the industry was fresh. Potentially the languages that were brought over from the 1970s weren't necessarily suitable for creating these 10 million lines of code as opposed to the 1 million. And the answer to that, I think, was the introduction of object-oriented programming. So you had this capability where developers could model their code in terms of abstraction and encapsulation. They could create reusable blocks of code. The code could be easily understood, and with this ease of understanding actually has an offset that you're going to potentially reduce defects. Apple kind of went through a rise and a bit of a fall. Steve Jobs left the company. He went on to form Next. But one of the things he did whilst he was at Next, besides producing an incredibly expensive computer, was that he looked at this problem and he adopted Objective-C. Now, Objective-C was a superset of C, so in some ways it was compatible, but what it tried to do is take the principles of Smalltalk and layer them on top of C, giving this object-oriented approach. And SQL as a language was created. It became a standard. So in 1987, SQL became the standard from the American National Standards and also an international standard. And it was designed by Donald Chamberlain and Raymond Boyce. Now, the concept behind this, why they realized there was a problem, was the way that they had to interact with relational databases. Using the codicil standards implied that you had to use a heavy mathematical formulaic approach. You had to traverse these trees of documents quite manually, and it just didn't sit right. And it was when Ted Codd from IBM, who was the acclaimed as the inventor of this hierarchical database structure, he was having a chat with him, and he said, sure, you can express a question by writing a navigational plan, but if you think about it, the navigational plan isn't the essence of what you're trying to accomplish. You're trying to find an answer to some question, and you're expressing the question as a plan for navigating. Wouldn't it be nice if you could express the question at a higher level and let the system figure out how to do the navigation? So Boyce and Chamberlain, they thought about this, and they were like, well, it's true. There should be a higher level abstraction. And this led them on to working on Square, which then culminated in SQL. And this is quite important as well when we look at the evolution of software languages, because we started to move away from this very sort of mathematical base and more into abstractions. We started to think about things on a slightly higher level. The 1990s. I think this is my favorite decade ever, right? Not at least because I heard two of my most favorite albums in the 1990s, Nirvana's Nevermind and Doolittle's Pixies. But I also graduated from university, and I also connected my computer to the internet for the first time. And the World Wide Web was going to be one of the primary drivers of change in this decade. Everything had to be connected. Everything had to be online, and it had to be accessible. New languages were cropping up. We started to see scripting languages such as PHP and ASP. Perl became incredibly popular. And we can't ignore the work that Tim Berners-Lee did. I mean, Tim created the internet. Well, not solely, but he had a major part to play in this. He coined the term the World Wide Web. His research led to HTTP and HTML. We also, the 1990s, we got the single market currency. And I'm not going to talk about Brexit because that just makes me sad. But we had some great things as well. Linux was released. Windows 3.1. The industry was changing. Things were advancing at a terrific rate. And as a developer, I got my favorite tool that's ever been invented. Google. But we also had some incredible innovation. So AWS, Amazon. Amazon didn't invent e-commerce, but what they did was they found a formula to make it work. They made it good. And the interesting thing is that the learnings that they got from operating their own e-commerce at massive scale would lead them to disrupting the industry once again with another great innovation in the next decade. So we had these scripting languages. And I think the scripting languages is really important because what we started to do was we started to move these applications in some ways back to the concepts of this multi-tenanted mainframe, but we were building these internet-enabled applications which were shared by multiple users. But the scripting languages weren't necessarily optimized for performance. In the early days, we didn't necessarily have caching, but what they did enable us to do is they enabled us to deploy software. So you could take a slightly more measured approach to risk. I didn't have to worry so much about making changes when all I had to do was FTP a file to a server. I didn't have to go potentially drive a car, get on a plane to a data center. It gave me a capability to work faster, to iterate faster. And object-oriented languages were really starting to kick in. Java came out in '95. It started to kind of move us to more of a thinking of distributed multi-tier computing. People were doing things like using ASP front ends and COM or ActiveX back ends. You know, we're thinking already about separating things up, breaking things down into manageable chunks. And of course, the Gang of Four book. This book still holds weight today. I mean, the patterns that were set out in here are still very, very, very usable and applicable. But what they were trying to do was they were trying to set out a way of commonality that as an industry, we could work better. We could design software which was maintainable and understandable. And Java, I mentioned it briefly, but we've got a lot to thank for in the 1990s for the Java project. I think because it was this first-class citizen of object-oriented principles, it started to kind of change the way that languages were evolving. It was also virtual machine backed. So unlike a sort of a compiled language, it would have to be recompiled dependent on the architecture that you were going to run it, Java allowed you to kind of build once and run almost anywhere. It introduced concepts around garbage collection. So it was kind of like offsetting the mental load of developing software into the runtime and allowing the developers to start thinking about the sort of the productive features that actually mattered. They introduced concepts like JUnit and testing frameworks, serverless. We had this sort of foundation and concepts around service-oriented architecture. Again, breaking down our applications, Java Beans, introducing the concepts of reusability. And actually, if you were developing software in Java in 1995, most of that knowledge is probably still relevant. The pace of change has been pretty glacial. But we can't really talk about the 1990s without talking about JavaScript. And originally, when Netscape sort of brought out this language, it was used, well, to kind of make things blink and scroll across a screen. It was fairly lame, but it gave a level of interactivity. It took the kind of the concepts that people were doing with early scripting languages and started to allow them to make things more dynamic, more interactive. Of course, Microsoft kind of threw a spanner in the works. They came up with a competing standard, and that introduced the whole browser wars, but it was still an incredibly interesting evolution. So the 2000s. Another period of major evolution. So this was the decade when writing software became cool. We had this kind of great gold rush again, which unfortunately ended up in the bubble bursting, but we had some really interesting companies spring up that did a hell of a lot for our industry. So Facebook was launched in 2004, Twitter in 2006. Everything had to be a website. We also had Flash, but I'm not going to talk about that because I'm still in therapy. But the interesting thing is that these companies were actually starting to drive some of the patterns and the practices that we were all using. They were taking their learnings and they were making it outwardly open for people to consume. It wasn't all good. We had some irresponsible lending. We had subprime mortgages. We had a banking crash, a global bailout. All of that driven by corporate greed. But then we had some great stuff as well. We had this embracing of software engineering, as a craft. So Kent Beck, he wrote TDD by example. You had Bob Martin, who wrote Patterns, Principles, and Practices, and Clean Coder. And the Agile Alliance formed. So we started to get techniques like Agile, which obviously Scrum and Kanban, and XP. So again, this is a massive drive in improving the quality of our software. And Kent Beck, in Extreme Programming, kind of analyzed and looked at these points and identified that these are areas where software was going wrong. So things like stuff's going into production, but it's full of defects. Features are not necessarily needed. XP, although, wasn't necessarily about code itself. It was the process of creating that code to create the quality and to create the business value. We had just-in-time development. We were thinking about our features differently. We wouldn't spend years analyzing a project, but we would sort of take things in shorter, smaller chunks. We want to realize that business value. And TDD's back on the scene again, because when you've got this kind of churn that an agile environment is imposing on you, you've got to have trust in your code. And code quality became a really big deal. Continuous integration. Like, this appeared. 2004, Sun Microsystems released Hudson, which, thanks to a lawsuit by Oracle, was renamed Jenkins. But it's the principle. It's that principle of quality, of constantly assessing and testing your code base. And the iPhone. So this literally started the new gold rush. Now, whether you love or hate Apple, we've got to look at the important social change that happened with the introduction of the iPhone and Android and the whole sort of mobile ecosystem. What it did was it put the World Wide Web in every single person's pocket. Now, not a lot of people would have been connected to the internet. The iPhone gave that opportunity. And what was interesting about the mobile technology and the rise of mobile technology was that it didn't just give the opportunity to the developed world. More importantly, it gave the opportunity to the developing world. So where the possibilities that copper cables and fixed lines just weren't possible, it was actually really, really achievable with the mobile networks. And virtualization, the next pivotal shift in our journey. 2003, vSphere. Now, you'd had a kind of process isolation, which was capable under Linux, and that improved with the work that Google put into C groups, but it wasn't easy. It wasn't necessarily attainable. Now, with vSphere and virtualization, what happened was, as developers, we had this capability to run a production machine locally. It gave us the additional quality around testing. It gave us the capability to run consistent environments across our entire stack. And ultimately, it led the way to the cloud. So that learning that Amazon had from running its own infrastructure led to AWS. 2006. In 2008, Microsoft followed with Azure. For us, what this meant was we had this capability that we were thinking again about software. We were thinking about features. Infrastructure didn't take a back seat, but it became somewhat easier. We could do things like blue-green deployments, which weren't necessarily capable or affordable previously. And we also had the rise of the API. So originally using the sort of a Java project of an XML-based SOAP, I mean, XML is everything in Java, so it was quite natural. And later JSON, we now had the capability of decomposing our applications into smaller chunks and communicating across this common interface. What it also gave rise to, which is really important for us as an industry, is software as a service. We didn't have to build everything anymore. We could choose things off the shelf. We could actually use hosted services. Developers, again, are concentrating on unique features. And the world just became more open. So GitHub founded in 2008. And yes, you had SourceForge and things like that, but GitHub really drove things forward. It was the thing that the community got behind. And open source started to become really, really important to developers. New languages started to come onto the scene, like Ruby. And we started to assess a language not so much on the sort of the features and capability of the language, but on the packages and the community. And we started to assess these packages, not on the features, but things like code quality metrics. We were looking for things like test coverage. So this is, I think, probably the most exciting time in my career, the modern era. We've had some incredible leaps in technology. Now, I think there's a direct upheld belief that the quality of your code is directly related to your quality of life. If you've got a good code base, if you're not having to get out of bed at 2 o'clock in the morning to fix bugs, you're going to be happier. By applying the sort of the things that we've learned in the past by following this progression of quality and by using virtualization, it actually started to give a benefit to us in terms of quality as life, not just in technological advancement. And one of the pivotal shifts in this was the foundation and the introduction of Docker in 2013. It really leveled up vSphere. I mean, where we had the capability of being able to use things like C groups to sort of have process isolation for CPU, memory, file system that was easily utilizable. It allowed us to further decompose our applications into microservices. And again, Google, Facebook, Twitter, they were kind of leading the way in this. Netflix too. I mean, Netflix has been fundamental in some of the patterns and the learnings that we've had. And let's get back to Microsoft, because they've been very, very much pursuing their own track for the last couple of decades. And Steve Ballmer, he hated Linux. He saw it as the biggest threat to Microsoft and desperately wanted to kill it. Thankfully, in 2014, Satya Nadella replaced him. Now, this is a real pivotal shift because Satya embraced Linux. And today, you'll find that about 40% of all compute that's running on Azure is Linux-based. And in addition to this, they started a trend of large enterprise organizations giving back to the community by contributing to open source rather than trying to compete with it. We get schedulers. So Twitter put a lot of work into Mesos, which is probably the sort of the first production grade scheduler. But at the same time, Google were taking a lot of the learning that they had on their own internal scheduler with Borg and were putting that into Kubernetes. And infrastructure just started to get more complicated. We were using the cloud, and the cloud providers provided APIs and interfaces, but it all just got a bit messy. So we had this wonderful rise of concepts of infrastructure as code. Companies like Chef, like Puppet, my own Terraform, they started to try and solve the problem that had been solved with object-oriented in our programming languages by creating this clear and concise declaration of infrastructure defined as code. We discovered that the old SOA patterns just weren't cutting it. We needed to find a way to manage things like service discovery, load balancing, circuit breaking. And we started to shift again to patterns like CQRS, domain-driven design, loosely coupled event-based systems rather than leveraging these sort of synchronous APIs. And insourcing became popular. It was no longer fashionable to outsource everything. Companies realized that you had to have a development capability. And because of that, again, when you own the application lifecycle, quality generally follows. It's not over. I mean, the cloud currently accounts for about 40% of all compute. AWS have got the lion's share of this, but look at the chart and see the difference that's happened in the last 12 months. I think it's going to be really interesting to see what's going to happen over the next 12 months. Can the competing clouds keep up with AWS in terms of features and start snatching away that share? And languages, we've got some new languages. We've got things like Go and Rust and Python, Swift, Kotlin. Some of these are solving the problems that we face today. Go and Rust, very much about this very sort of high throughput, highly concurrent distributed computing. Languages like Swift, trying to solve the problem that Objective-C was not necessarily accessible for a large amount of developers. Python is exploding. I mean, machine learning, data science, Python has been incredibly adopted in those communities. Kotlin kind of came on the scene, and whilst it's a nice language, I genuinely don't really have a problem with Java. I find that Kotlin is potentially an approach by Google to distance itself from Oracle rather than solving a fundamental need. But we also have concepts like static code analysis. Again, we're back on the quality. We want to raise our game. So I think things like memory management, garbage collection, they're incredibly important for us. But when you're choosing a language, you've got to think about the life cycle. You've got to think about what that means for the life of the application, not just your time working on it. So let's have a stab at the future. Okay, so the first problem. The first problem we face in tech is diversity. And I think this is something we need to change. We need more diversity. We need the difference of opinions that are going to drive the sort of the technical advancements. We need that cultural mix-up. And this is your problem to solve. Everybody can do a bit to solve this. From a technological perspective, serverless, it's going to be king. Things like using functional service, decomposing those microservices even smaller, having this capability of globally distributed but managed infrastructure. Things like Kubernetes as an interface. You wouldn't necessarily maintain a Kubernetes cluster, you just interact with it. And I think consumer hardware sales are going to almost become extinct when it comes to tin. So you've got companies like Dell EMC who are moving towards more of a, hey, don't buy a server, put it in Dell Cloud. Now this is attractive from a business perspective because it moves the costs into an operational cost away from capital expenditure. Languages, again, if we look at the sort of the growth, we've got Rust up there, Go's up there, R and Python. And taking a close look at Python, let's look at some of the most popular frameworks or the increases in frameworks on Python. Again, it's the sort of the data science frameworks. It's Pandas, it's NumPy. And this is definitely sort of showing and highlighting where the industry is going. We're going distributed computing. We've got Rust and Go. We're going machine learning, data science. It's not just about trying to sell me stuff. It's about solving a problem that's good for the industry. So tooling, that needs to develop. It needs to catch up with where we are. There's certain areas which are administering and interacting with clusters, things like Kubernetes. It can do with a boost. Service meshes, offsetting the complexity of things like circuit breaking, load balancing, that should be just done for us. We've got infrastructure as code, and I think we'll see the increase of that. But I think also we're going to start to look at things like policy as code, especially in enterprises. We're going to need to look and codify the way that people interact with infrastructure, not just how you codify to define it. And managed services are just going to be the norm. You're just going to push your code into the cloud, and it will kind of just work. So for me, I'm thinking that the next generation is going to be my last in the industry, because what I want to do is I want to move into an area of education. I want to be able to help the next generation to be able to foster the diversity, be able to bring up the next level of talented developers. And I hope everybody else follows me with that. I think it's our social responsibility as developers to take what we know and to teach that to others. Whatever happens, I think what we can see is that the patterns that we've seen over the last few decades, this advancement but following the common theme around easy of deployability, about quality, it's going to be very bright, and I'm very, very enthusiastic. So with that, I want to say thank you so much for listening to me. And any questions?
So thank you, Nick. We have time for one question.
Oh, yes.
Only one.
What about JavaScript?
So this is interesting. So I think JavaScript, when you look at the trends, so JavaScript obviously rose to prominence around server-side development. I mean, it sort of became, Node.js became incredibly popular. I think this was driven by a full stack development approach because developers who are building maybe front-end applications could also interact with the back-end. As a language, when I look at it, I find that it needs to undergo some evolution. So you've got things like the latest ECMA standard and things like TypeScript, which can improve the quality inside the code, make it easier to read and easier to interact with. I think JavaScript is just kind of, it's a little bit out of control. I mean, there's a lot of competing frameworks. One of the things that frustrates me about the language is that I look at something like React, and I liked Angular, and I look at React and I don't really agree with this. I don't like the mixed pattern of introducing interface code, so presentation logic, into my actual code itself. But this is what the industry is using. So I'm like, okay, I'll bite the bullet, I'll learn React. And like, seems like 12 months later, it's all about Vue.js. So I think JavaScript's always going to be there. We're definitely building more applications which are sort of browser-centric, but I would genuinely like to see that JavaScript remains in the domain for where it was intended, which is in the browser, and that the sort of the back-end languages are held by the more sort of what I see is sort of capable and easier to work with languages, Go, Rust, Java, Python, if you want to use stuff like that.
Okay, thank you, Nick.
Thank you.